Hello everyone. Today we will see about recurrence relations. So before defining the recurrence relation, let's define what a sequence means. The sequence is just it's an arrangement of an object or a set of numbers in a particular order, following with some rules, just like these ones, which denotes the term of sequence, where the numbers 1, 2, 3, 4 denotes the position of the terms of the sequence. And the sequence can be defined based on the number of the terms, either as finite or it can be infinite. Just as an example of a sequence of positive integers, sequence of positive even integers, sequence of power of 2, sequence of Fibonacci numbers, which is just a special type of sequence, which is obtained by the term is obtained by the sum of the previous two terms, and which is 0, 1, 1, and then 2, 3, 5, 8, and so on. And the other one is reciprocal of positive integers, just like this one. Reciprocal of positive integers is just an example of a sequence. And when you come to the lesson, which is about recurrence relation for a sequence n is an equation that expresses an in terms of one or more of the previous terms of a sequence, namely a0, a1, an, an minus 1 for all integers n with n greater than or equal to a0 and where a0 is a negative integer. A sequence is called the solution of a recurrence relation if it is in terms satisfying the recurrence relation. Clearly, you can see that the sequence is a solution of recurrence relation if it satisfies its recurrence relation. Examples of a recurrence relation, you can see. Let's define first what a linear recurrence relation means. A linear recurrence relation is an equation of the form like this one, for n greater than or equal to k, where c0 n, c1 n, ckn, and fn are functions of n, and subscripts n and k are non-negative integers. Based on the definition, the recurrence relation will become linear, nonlinear, homogeneous, non-homogeneous, constant coefficient, variable coefficient, and one recurrence relation may become either of this. Sometimes it may contain and it may hold more than two categories. It may become linear with constant coefficient. It may homogeneous. It may become nonlinear, non-homogeneous, constant coefficient, or it may become linear, homogeneous, and variable coefficient. So a given recurrence relation may have more than two category of recurrence relations. So if the recurrence relation coefficients C0 and C and K are different from 0, then the recurrence relation is said to have the degree K recurrence relation. And if the coefficients C0 up to Ck are constants, then the recurrence relation is said to be a linear recurrence relation with constant coefficient. Otherwise, it's called recurrence relation with variable coefficient, which means that the coefficients C0 up to Ck are functions of n. If the function fn is 0, then the recurrence relation is said to be linear homogeneous recurrence relation. Otherwise, which means that if fn is different from 0, then the recurrence relation is said to be non-homogeneous recurrence relation. And the other definition is the recurrence relation is said to be non-linear. Recurrence relation is said to be non-linear if there is a product of two numeric functions, or at least one term has a power greater than 1. If at least one term has a power greater than 1, then that recurrence relation is said to be a nonlinear recurrence relation. Let's see an example for these definitions. For example, you can look at the first example. You can see that it's linear, and you can see the coefficients are constant, and you get this one, fn is 0. Therefore, and it's also it has degree 2. It's a degree 2 recurrence relation. So linear, homogeneous, constant, coefficient, degree 2. The second example is, you can see that there is no power greater than 2n, there is no product of two numeric functions, so it's linear. The coefficients are constant, and fn is not 0, so that it is non-homogeneous. So it's linear, non-homogeneous, constant, coefficient, and its degree is 2. In the third example, you can see and here you can see this one. There is no power or product of the terms, and you can see the coefficients are variable, and the function fn is 0, therefore it's linear, homogeneous, variable coefficient, and it's degree 2. In the fourth example, you can see the fourth example here, there is no product of terms, or anything, there is no term which has greater than 2, greater than 1, and the coefficients, so it's linear, and the coefficients are, you can see, constant, and fn is different from 0, it's non-homogeneous, and the degree of the recurrence relation is 3. The degree of the recurrence relation is 3. The fifth example, you can see that the terms of the sequence, this recurrence relation, one term has greater than 1 power, and there is a product of two terms of the numeric terms of the recurrence relation, so it is nonlinear. The coefficients are constant, and it's homogeneous, since the fn is 0, and the degree of the recurrence relation is 2. The last example, you can see it's also nonlinear, because it one term, at least one term, has greater than 2 power, and the coefficients are constant, and it's nonlinear, non-homogeneous, therefore nonlinear, non-homogeneous, constant, coefficient, and degree 2. The other one is a solution of a recurrence relation. A solution of a recurrence relation is an arbitrary function which satisfies a recurrence relation. Let's see this definition with an example. Given the sequence an is equal to n start from 0 to n, where n is to the power of n, then show that this sequence satisfies the recurrence relation, this recurrence relation. So to show that the sequence satisfies this recurrence relation, we substitute the sequence on the recurrence relation, and if it satisfies the recurrence relation, then it's the solution of the recurrence relation. So the sequence is this one. Now, when you substitute this recurrence relation, an is, you substitute here, then 2 times an minus 1, the an minus 1 term of the sequence is 2 times an minus 1 is this one. So 2 times to the power of n times to the power of n minus 1. When you split this one, you'll get this term. You'll get this term. So 2 to the power of minus 1 is cancelled by 2, then you will get to the power of n, and this one is an. Hence, an which is equal to an, so that an to the power of n is a solution of the recurrence relation. Another example is let's C1 and C2 are arbitrary constants, then show that this sequence satisfies the recurrence relation, this one. So the sequence is an, which is equal to C1 to the power of n plus C2 times the power of n. And the recurrence relation is an minus 7, an minus 1 plus 10, an minus 2, which is equal to 0. Now we have this one. An is C1 to the power of n plus C2 times the power of n. Then n minus 1 is C1 to the power of n minus 1 plus C2 times the power of n minus 1. And n minus 2 is C1 to the power of n minus 2 plus C2 times the power of n minus 2. Now substituting these terms, is on the recurrence relation. On the recurrence relation, we get the following. So substituting this one is an term, and substituting the an minus 1 term on the sequence reconstruction, and substituting the an minus 2 term on the reconciliation, you get this one. Now, collecting those coefficients which have C1, you'll get this one. C1 to the power of n minus 7, C1 to the power of n minus 1 plus 10, C1 to the power of n minus 1, sorry, minus 2, plus C2 for collecting C2 terms, those terms which have coefficient C2 5 to the power of n minus 7, C2 5 to the power of n minus 1 plus 10, C2 5 to the power of n minus 2. Now, taking common C1 to the power of n minus 2 from the first, from this part, taking C1 to the power of n minus 2, from the first term, you'll get 4, and from the second term, 7 times 2, which is 14, and from the second term, you'll get 10, plus, when taking C2 5 to the power of n minus 2 on this part, taking common, you'll get C2 5 to the power of n minus 2. So on the first term, what remains is 25, and the second term minus 7 times 5, which is 35, plus on the last term is you'll get 10. So adding these terms, adding the remaining terms here, you get 4 plus 10 is 14 minus 10 minus 40 is 0. 25 plus 10 is 35 minus 35 is 0. So the sequence satisfies the recurrence relation. Hence, the given arbitrary sequence is a solution of the recurrence relation. Another good definitions in recurrence relations are initial or bounded conditions of the recurrence relation. So these terms, these values are values which are given with the recurrence relation depending on the arbitrary constants. If the arbitrary constants are 2, then we may have 2, we will have 2 initial conditions. If the arbitrary constant is 1, we will have 1 initial condition. So these are requirements that satisfy the recurrence relations are initial conditions. So initial conditions are conditions that satisfy the recurrence relations. And a solution involving many arbitrary constants as the order of the relation is a general solution. So the number of arbitrary constants depends on the order of the solution. If the order of the recurrence relation is 2, we have 2 arbitrary constants. If the order of the recurrence relation is 1, we have 1 arbitrary. The solution of that recurrence relation will have 1 arbitrary constant. So if the order of the recurrence relation is 3, then the solution of the recurrence relation will have 3 arbitrary constants. So in general, the solution involving these arbitrary constants is said to be the general solution of the recurrence relation, and any solution obtained from the general solution by assigning particular values to one or more arbitrary constants is called a particular solution of the recurrence relation. So substituting those initial conditions on the solution, the general solution of the recurrence relation will give the arbitrary constants, and so substituting those arbitrary constants will obtain the particular solution of the recurrence relation. For example, from the above example, we proved that n, which is equal to c1 to the power of n plus c2 5 to the power of n, is a general solution for the recurrence relation. This one, then given 2 initial conditions, a0 is equal to 10 and a1 is equal to 41, what will be the particular solution for this recurrence relation? So substituting n is equal to 0 and n is equal to 1 on the solution on the sequence, 10, which is equal to a0 is equal to c1 to the power of 0 plus c2 to 5 to the power of 0, which is equal to c1 plus c2. And substituting n is equal to 1, 41, which is equal to a1, which is equal to c1 to the power of 1 plus c2 5 to the power of 1, which is equal to 2 times c1 plus 5 times c2. So we have 2 equations. We obtain 2 equations. So solving these two equations simultaneously or by substitution, we get the solution to C1, the solution for the arbitral constant C1 and C2. So from the first equation, we get C1, which is equal to 10 minus C2, and substituting this C1 on the second equation here, we get the value of C2. So substituting C1, 41 is equal to 2 times 10 minus C2 plus 5C2, which is equal to minus 2C2 plus 5C2 plus 20, which is 3C2 plus 20. So 41, which is equal to 3C2 plus 20. And rearranging this one, we get 7C2, which is equal to 21, so which implies C2 is 7. And we know that C1 is 10 minus C2, so substituting 7, 10 minus 7, we get C1 is 7. Therefore, AN, which is equal to 3 times 2 to the power of n plus 7 times 5 to the power of n. 5 to the power of n is a particular solution to the recurrence relation. Start from the first order linear homogeneous recurrence relations. As a definition, the first order linear recurrence relation is defined like this one. The first order linear recurrence relation is an equation of the form like this one, or you can write such a way, where C is any arbitrary constant. One way to solve such a recurrence relation is by substitution or an iteration method. In this method, a given recurrence relation is used over and over again for different values of n, where n plus from 0, 1, 2, until we obtain a closed form formula for the recurrence relation. So that formula will be the solution for the recurrence relation. As we have defined last time, the solution for the recurrence relation is a sequence that satisfies the recurrence relation. So let's see this one with an example. The example says solve the recurrence relation, which is an, which is equal to 2 times an minus 1 with an initial condition a naught, which is equal to 1. So using an iteration method, you will substitute n is equal to 1, 2, 3 up to the nth term. Then we will get a recursive formula which is close to the solution of the given recurrence relation. So when you are n is equal to 1, it becomes 2 times a naught when we substitute n is equal to 1. And when we substitute n is equal to 2, it becomes 2 times a1, where a1 is this one, which is 2 times 2a naught, which is to the power of 2a naught. And a3 will be 2 times a2, then a2 is, we know that the a2 is to the power of 2a naught, then a3 is to the power of 3a naught. So in such a way, an will be 2 times an minus 1. But an minus 1 is defined before, then which will be to the power of n naught, to the power of n naught. Hence, an, which is equal to the power of n naught, is a general solution to the recurrence relation. And since the initial condition is given, we can find the particular solution to this recurrence relation. So substituting a naught is equal to 1 on the general recurrence relation, we get an, which is equal to the power of n, is a particular solution to this first order recurrence relation. So this is the solution for the first example. Let's add another example. Solve the recurrence relation. Solve the recurrence relation an, which is equal to 2 times n minus 1 plus 1 with an initial condition a1 is equal to 1. So by using an iteration method, putting n is equal to 1, 2, 3 in such a way, a2, which is equal to 2a1 plus 1. So a3 will be 2a2 plus 1, but a2 is 2a1 plus 1. Substituting it, you will get this one to the power of 2a1 plus 2 plus 1. So A4 will be 2 A3 plus 1, which is equal to 2 times A3 is this one. So 2 to the power of 2, A1 plus 2 plus 1 plus 1, which is equal to 2 to the power of 3, A1 plus 2 to the power of 2 plus 1 plus 1. And A5 is 2 times A4 plus 1, that A4 is defined here, then 2 times A to the power of 3, A1 plus 2 to the power of 2 plus 2 plus 1 plus 1. So which is 2 to the power of 4, A1 plus 2 to the power of 3 plus 2 to the power of 2 plus 1 plus. So clearly you can see that A5, which if it is AN, then you will reduce 1, then on this term you will reduce 2, n minus 1, n minus 2, n minus 3, such plus something. So the nth term will be, an will be 2 to the power of n minus 1 plus 1, which is 2 to the power of n minus 1, a1 plus 2 to the power of n minus 2 plus 2 to the power of n minus 3 plus 2 plus 1. So we can write this one in such a way, 2 to the power of n minus 1, a1 plus 1 plus 2 plus 2 to the power of 2 plus 2 to the power of n minus 2. And we know that 1 plus 2 plus 2 to the power of 2 plus 2 to the power of n minus 2, which is equal to 2 to the power of n minus 1 plus 1 in basic mathematics for the freshman university students here. And since A1 is 1, so since A1 is 1, AN, which is equal to the power of n minus 1 plus 2 to the power of n minus 1 minus 1. See, which implies that AN, which is equal to the power of, adding these two terms, you get AN, which is equal to the power of n minus 1 is the particular solution for this, the particular solution for the recurrence relation. So another example, let's look at another example. Solve the recurrence relation, an, which is equal to an minus 1 plus n with the initial condition a1 is equal to 2. Similarly, substituting n is equal to 1, 2, 3, up to n, we will get the closed form solution for this recurrence relation. So when n is equal to 2, a2 is equal to a1 plus 2. When n is equal to 3, a2 which is plus 3, but a2 is a1 plus 3, so which is a1 plus 2 plus 3. a4 is a3 plus 4, but a3 is a1 plus 2 plus 3, which is a1 plus 2 plus 3 plus 4. In such a way, an is an minus 1 plus n, which is a1 plus 2 plus 3 plus 4 plus like that, plus n. So which is the general solution, and substituting the initial condition, a1 which is equal to 2, we get a particular solution. So now to find that particular solution, let's replace 2 plus 3 plus 4 plus this one. So 2, substituting after that, substituting a1, you'll get 2 plus 2 plus 3 plus 4 plus n. Now let's split 2 as 1 plus 1. 2 as 1 plus 1, then 1 plus 1 plus 2 plus 3 plus 4 plus this one is this term, as you have learned in basic mathematics of freshman course. This term is equal to this value. So the an term, the an is the particular solution for this recurrence relation. An is given by 1 plus n times n plus 1 over 2 is the particular solution for the recurrence relation. So on the next section, we will see the solution of second order homogeneous linear recurrence relations. Hello everyone, today we will see about the solution of second order linear recurrence relation with constant coefficient. So let's define first what's the homogeneous linear recurrence relation with degree k. A linear degree k homogeneous recurrence relation with constant coefficient is a relation of the form like this one. We see this. So this is a homogeneous linear recurrence relation with degree k, where the constants C1, C2, C are constants, where C1, C2, Ck are constants. Now, based on this one definition, we can we can take a second order homogeneous linear recurrence relation is represented by this one. It's represented by this one. Or you can write in such a way. You can write in such a way. You can write in such a way where this expression is the definition expression of recurrence relation. As we have defined before in last sections, recurrence relation is an expression of the nth term of a sequence in terms of one or more than one previous terms. So we can express a second order linear recurrence relation with constant coefficient, either this one or this one, or where C1 and C2 are constants. Now, to find the solution to this second order linear homogeneous recurrence relation, let's guess a solution to this recurrence relation. Let's assume this one will be the recurrence, an initial guess to the solution to this recurrence relation. So now substituting this trial solution on the recurrence relation, here, you will get this one, r to the power of n when you are substituting on the an term, and then c1 r to the power of n minus 1 when we are substituting on c1 times an minus 1, and the last one is c2 plus c2 r to the power of n minus 2, which is equal to 0. Then taking common r to the power of n minus 2, we'll get this one. Taking from this one, taking r to the power of n minus 2, you'll get r to the power of n minus 2 into what's left in this term. What's left on this term is r squared, and what's left on the next term is c1r, and on the last term we will get c2. Then we get this quadratic equation. This quadratic equation is said to be the characteristic equation or the characteristic polynomial to the recurrence relation. And you can see that the roots of this characteristic equation are 2. The roots of this characteristic equation are 2 because it's a polynomial function of degree 2. So a polynomial function of degree 2 has 2 roots. The roots of the characteristic equation the roots of this equation may be similar, or they may be distinct, or they may be complex coordinates. Now let's see the first case, that if the characteristic polynomial or the characteristic equation has 2 distinct roots, alpha 1 and alpha 2, then we say that the general solution to the recurrence relation is this one. General solution is this one. Now let's see an example for the solution of the recurrence relation which has distinct roots. Now let's find the solution to the recurrence relation given by an is equal to 2 times an minus 1 plus 3 times an minus 2, with an initial condition n is equal to 0 and a1 is equal to 8. Clearly, you can see that it's a homogeneous linear constant coefficient recurrence relation. So now we can rewrite the equation in this form. Let's rewrite the equation in this form. So which is taking those terms, previous terms on the an side. Then the characteristic equation to this equation is given by r squared minus 2r minus 3, which is equal to 0. Now to find the roots of this equation, what are the numbers which gives where the sum is minus 2 and the product is minus 3. So their sum is minus 2 and the product is 3 is minus 3 and positive 1 again. Then by factorizing, you will get this one. So the roots of the characteristic equation is r1 is equal to minus 1 and r2 is equal to 3. Hence, the general solution to the recurrence relation is this one. To determine the coefficients since we have given initial conditions to determine the coefficients of this general solution and obtain the particular solution of the recurrence relation, we can substitute the initial conditions. So A naught is given, which is equal to 0, while A naught is when the value of n is equal to 0, and A1 is when the value of n is equal to 1. Then substituting n is equal to 0 and 1 on the general solution, we get the values of these constants. So when n is equal to 0, you'll get A naught, which is 0, p times minus 1 the power of 0 plus q times 3 the power of 0. Minus 1 the power of 0 and 3 the power of 0 are 1, so p plus q is left. So 0 is equal to p plus q. And when n is equal to 1, we get 8. A1 is 8, which is equal to minus p, which is p times minus 1 to the power of 1 plus q times 3 to the power of 1. So minus p plus 3 times q is obtained. Now, from the first equation, we can get that p, which is equal to q. We can obtain this one, p, which is equal to q. So, or p is equal to minus q is equal to minus p, or p is equal to minus q. Then for substituting this one on the second equation, you will get this one, 8, which is equal to minus p plus 3 times minus p, which is equal to 8, and plus which is equal to 8 is equal to minus 4p, which is minus p minus 3p is minus 4p, and divided by minus 4p, which is equal to minus 2. And since p is equal to minus q, or q is equal to minus p, since p is minus 2, q becomes positive 2. Q becomes positive 2. Hence, the particular solution to the recurrence relation is given by this one. So this is the solution to the recurrence relation. And we have said that the solutions to the recurrence relations are always sequences. The solutions of the recurrence relations are sequences. Let's see another example. Solve this recurrence relation given by n is equal to 2 times n minus 1 plus 8 times n minus 2 with the initial conditions a naught is equal to 1 and a1 is equal to 2. So these initial conditions are used to find the constant terms of the general solutions of this recurrence relation. So let's rewrite first this equation in the form like this one. A is equal to minus 2an minus 1 minus 8an minus 2, which is equal to 0, which is equal to. So the characteristic equation to this second order linear recurrence relation is given by r squared minus 2r minus 8, which is equal to 0. Now, the roots of this characteristic equation, will be what are the numbers whose sum is minus 2 and whose product is minus 8. Their sum is minus 2 and their product is minus 8, which is which is plus 2 and minus 4 are. Their sum is minus 2 and their product is minus 8. So r, when we are factorizing r plus 2 times r minus 2, r minus 4 is equal to 0, then the roots are minus 2 and minus 2 and 4. Hence, the general solution to the recurrence relation is this one. The general solution to the recurrence relation is this one. So which is given by this one. This is the general solution. This is the general solution. To determine the coefficients, we can substitute the initial conditions. N is equal to 0 when a naught is given us 1, so a1 is 2. Then let's substitute n is equal to 0. So when n is equal to 1, 1 plus p plus q. 1 is equal to p plus q, and when n is equal to 1, we get 2, which is equal to minus p plus 4q. Now, from the first equation, we can obtain this one. From the first equation, we obtain this one. So substituting this one on the second equation, we get 2 is equal to minus p minus 2p plus 4 times 1 minus p, which implies 2, which is equal to 4, which is when I multiply this one. 4 times 1 is 4 minus 4p, so which is minus 6p. So 4 plus 2p minus 4p is 6. So 2 is equal to 4 minus 6p, which implies that p, which is equal to 1 over 3. Then since p is equal to 1 over 3, then we can determine q is 1 minus p. So which is 1 minus p, which is equal to 1 minus 1 over 3, which is 2 over 3. Hence, the particular solution to the recurrence relation. So the particular solution to the recurrence relation is this one. This one. And the other example, let's take another example. Solve the recurrence relation of the form like this one. An is equal to an minus 1 plus 4n minus 2 plus 4n minus 3 with initial conditions a0, a1, and a3. Clearly, you can see that the recurrence relation is a third order recurrence relation with constant coefficient, which is homogeneous. It's a third order recurrence relation with a constant coefficient. So we can rewrite this equation in this form: n plus n minus 1 minus 4n minus 2 minus 4n minus 2, which is equal to 0. Then the characteristic equation to this recurrence relation is r cubed plus r squared minus 4r minus 4, which is equal to 0. By the first, by applying rational zeros theorem, the possible roots of the equation are the factors of the constant term and the factors of the leading term, of this polynomial. The factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4, and the factors of the leading coefficient 1 is plus or minus 1. So the possible roots of this equation, this characteristic equation, will P over Q, the factors of the constant term over the factors of the leading coefficient. So which is plus or minus 1, plus or minus 2, or plus or minus 4. Clearly, by substituting, by guessing from these possible roots, by substituting the first one, minus 1 to the power of 3 is minus 1, plus minus 1 to the square is positive 1, so minus 1 plus 1 is cancelled by themselves, and minus 4 times minus 1 is positive 4, minus 4 is cancelled by itself, so that it gives 0. Therefore, it's the root of the first root of the characteristic equation. So dividing the polynomial, dividing r cubed plus r squared minus 4 minus 4r minus 4 is equal to 0 by r plus 1, we get this one. Dividing that, we get this equation. Then r squared minus 4 is so a perfect square, which is just it's just a quadratic equation, which is a product of r minus 2 and r plus 2. Therefore, the roots of this characteristic equation are which this one, x is equal to minus 1, x is equal to 2, and x is equal to minus 2. So clearly, you can see that the roots of the characteristic equation are distinct roots, 3 distinct roots. So the general solution to the recurrence relation is given by this one. An is equal to r times minus 1 to the power of n plus p times minus 2 to the power of n plus q times 2 to the power of n. Now, since we have given 3 initial conditions, we can determine the roots of the characteristic equation. When substituting n is equal to 0, we get 0 is equal to r plus p plus q. When we substitute n is equal to 1, we get 2, which is equal to minus r minus 2p plus 2q. And when we are substituting n is equal to 2, we get 8 is equal to r plus 4p plus 4q. Solving the equation simultaneously, we get r is equal to 10 over 3, p is equal to minus 3, and q is equal to minus 1 over 3. Q is equal to 1. Hence, the particular solution to the recurrence relation is given by this one. Okay, on the previous class, we will see if when the characteristic equation has similar roots or identical roots of the recurrence relation. Thank you for today's class. Hello everyone. Today we will see about the solution of second order linear recurrence relation with constant coefficient. So from the definition, a linear degree k homogeneous recurrence relation with constant coefficient is represented by or defined by this one. Order k. C1, C2, Ck are constants. So it's a homogeneous. Recurrence relation with constant coefficients. And it's linear because there is no power or product of the numeric terms of the recurrence relation. From this definition, we can take a second order linear recurrence relation is represented by this one. second order linear recurrence relation is represented by this one, or you can represent this one by splitting the nth term and expressing it by the previous terms of the sequence, where C1 and C2 are constants. Now, to find the solution to this recurrence relation, we can start from the initial guess as a solution to this recurrence relation to be this term, Then substituting this sequence on the recurrence relation, you will obtain this one r to the power of n when you are substituting on the an term, then plus C1 r to the power of n minus 1 and plus C2 r to the power of n minus 2, which is equal to 0, subsequently substituting on n minus 1 and n minus 2 terms. Now taking the common term on this equation, which is r to the power of n minus 2, then we get this equation. R to the power of n minus 2 times r squared, which is what's left on this one, the remaining part from r to the power of n, when you are taking r to the power of n minus 2 as common, which is r squared plus C1 r plus C2. Now, you can see that by dividing r to the power of n minus 2 on both sides, you'll get that r squared plus C1 times r plus C2 is left, and this equation is said to be the characteristic equation or the characteristic polynomial to the recurrence relation. And clearly you can see that it is a quadratic function, and the roots of this quadratic function may be are 2. And these two roots may be identical, or they may be distinct, or they may be complex conjugates. Now, in this section, we will see the second case of the roots of the characteristic equation, when there are two equal roots, when the characteristic polynomial or characteristic equation has two polynomial roots alpha, then the general solution to the recurrence relation will be this one, which is an is equal to p times alpha to the power of n plus q times n. N is due to the repeated root of n times alpha to the power of n, will be the general solution, Let's see with an example. Solve the recurrence relation defined by n is equal to 4 times n minus 1 minus 4 an minus 2 with initial conditions a0 is equal to 1 and a1 is equal to 1. Now, the characteristic equation to the recurrence relation, is x squared plus 4x plus 4, which is minus, it's just to say minus 4x plus 4. Then what are the numbers where their sum is minus 4 and their product is positive 4? The numbers are minus 2, with the numbers are minus 2, minus 2. So x minus, this one, so x minus 2, the whole square, which is equal to 0. So which is a perfect square. So the root is x is equal to 2 with multiplicity 2. The root 2 is 2 times the roots of the characteristic equation. So the solution to the recurrence relation, the general solution to the recurrence relation, is given by an is equal to p times 2 to the power of n plus q times n times 2 to the power of n. N is added due to the repetition of the roots 2 times. Now, in order to determine the coefficients p and q, we can substitute the initial conditions, which is given associated with the equation, the recurrence relation. So when n is equal to 0, substituting n is equal to 0, you'll get a0. A0 is clearly 1. 1 is equal to a0 to the power of 0 plus q times 0, which is 0. When you're substituting 0, this term becomes 0. So 1 is equal to n is equal to p. So the p value is 1. And when we substitute n is equal to 1, we get a1, and a1 is minus 1. So 2 times p plus 2 times q, but p is clearly, we obtain that p is 1. So q is rearranging the value, you'll get the q value, which is minus 1 over 2. Hence, the particular solution to the recurrence relation is given by this equation, which is n is equal to the power of n minus n over 2 times to the power of n, and taking to the power of n as common to the power of n, which is 1 minus n over 2 will be is a particular solution to the given recurrence relation. Let's take another example. Solve the recurrence relation. Solve the recurrence relation. N is equal to 6 times n minus 1 minus 9 times n minus 2 is initial conditions. Initial conditions. Mostly initial conditions are given with a question to find the particular solution of the recurrence relation. So before finding the particular solution, we are going to determine the general solution. Then from the general solution, substituting these initial conditions, we give the particular solution. So the characteristic equation to this second order linear homogeneous recurrence relation is given by r squared minus 6r plus 9, which is equal to 0. And the roots of this quadratic equation is obtained by finding the two numbers where their sum is minus 6 and their product is 9. So the numbers are minus 3 and minus 3. Their sum is minus 6 and their product is positive 9. So r squared minus 3, the whole square, r minus 3, the whole square, which is equal to 0. So r is equal to 3 is the root of the characteristic equation with multiplicity 2. With multiplicity, these two, multiplicity is just number of repetition, the number of how many times the root of the equation is repeated. It's just said to be the multiplicity of the root. So the solution to the recurrence relation is, since the root of the characteristic root of the roots of the characteristic polynomial or the characteristic equation are repeated, so we can use that one, so that the general solution to the recurrence relation is given by this one. A n is equal to p times 3 to the power of n plus q times n minus 3 to the power of n. Let's now determine the values of the constants so that we can get the particular solution. So substituting n is equal to for n is equal to 0, we get 2, which is equal to n naught is equal to p, because when we are substituting n is equal to 0 here, it makes the whole 0 value, so that p value is 2. We get 2, p value 2. Then substituting n is equal to 1 on this one, it becomes 5, which is equal to a1 is equal to 3 times p plus 3 times q. Then q, substituting the p value, which is 2, on the equation, we get q is equal to 1 over 3. Q, which is equal to 1 over 3. Here's the particular solution to the recurrence relation. The particular solution to the recurrence relation is given by this one. Now we will see on the next section about the case 3, which where the roots of the characteristic equation becomes complex conjugates of the recurrence relation. So linear degree k non-homogeneous recurrence relation is of the form like this one, which is of the form like this one. You see this, which is non-linear. And non-linear, you can see that fn is different from 0, where the coefficients c1, c2, cn are constants. That's why we call it a constant coefficient in linear non-homogeneous recurrence relation. So from this general definition, we can adapt the second order linear non-homogeneous recurrence relation with constant coefficient. So a non-homogeneous second order linear recurrence relation with constant coefficient is of the form this one, where the coefficient c1 and c2 are constants and fn is different from 0. Examples of non-linear non-homogeneous recurrence relations are an minus 3 an minus 1 plus 2 an minus 2, which is equal to n squared plus 1. You can see that the coefficients are constants and there is no product or power on the numeric terms of the recurrence relation, so it is linear. And since the function fn is different from 0, so it's non-homogeneous. Similarly, an minus 1 minus 6 an minus 2, which is equal to the power of n, is also another type of non-homogeneous linear recurrence relation. And the third example is an minus 3 an minus 1, which is equal to n times 3 to the power of n, is also another non-homogeneous. linear recurrence relation with constant coefficient, but this one, the degree of this example of non-linear recurrence relation is 1, and the other 2 are the degree of the recurrence relation is 2. Now, when we see this theorem, if ANP is a particular solution to the linear non-homogeneous recurrence relation with constant coefficient, then every solution of the form AN is equal to AN H plus ANP is a general solution to the linear non-homogeneous recurrence relation with constant coefficient, where the AN part, the NH part is the solution of the associated linear homogeneous recurrence relation. Linear homogeneous recurrence relation. So to find the solution of the non-homogeneous recurrence relation, we use the method of undetermined coefficient. The method of undetermined coefficient uses a guess solution to the particular solution of the non-homogeneous recurrence relation and determine the coefficients, the values of the coefficients in the general expression of the solution. So the trial solution or the initial guess to find the solution of the non-homogeneous recurrence relation depends on the functions that makes the recurrence relation non-homogeneous. So for instance, in the examples in here, the functions that makes the recurrence relation non-homogeneous is polynomial function. On the second example, it is an exponential function. The other one is the product of polynomial and the exponential function. So depending on the functions that makes the recurrence relation non-homogeneous, we can give an initial guess or trial solution to the recurrence relation. So when Fn is an exponential function, which means Fn is d times n in base a, there are two cases. If a is not the root of the characteristic equation to the homogeneous part, then the particular solution, the initial guess will be taken as n will be c times a, the power of n will be taken as this one. If a is a root to the characteristic equation to the homogeneous part with multiplicity m, then the initial guess will be taken as c times n, the power of m times n in base a, where n the power of m is the multiplicity of the root a, the multiplicity of the root a. And the other one is when the function fn is a polynomial function in the form like this one. If it is of the form like this one, then it has two cases. If one is a root of the characteristic equation to the homogeneous part, then the initial guess will be taken as c0 plus c1n plus c2n squared plus ck n the power of k. If one is a root, this one is when one is not the root. If one is a root to the characteristic equation to the homogeneous part with multiplicity n, then the initial guess or the trial solution to to find the particular solution will be taken as c0 plus c1n plus c2n squared plus ckn squared times n the power of m. And the third case is when fn is a product of exponential and polynomial function. So we have the two cases similarly. If one is not the root of the polynomial, the characteristic equation to the homogeneous part of the recurrence relation, then this one will be taken as the trial solution to find the particular solution of the non-homogeneous part. And if one is the root of the characteristic equation with multiplicity n, then the particular the trial solution to the recurrence relation will be n0 plus c1n plus c2n squared plus ckn the power of k times n the power of m times n in base a will be taken as this one. So we have seen these three cases. Let's see with an example. Let's see with an example. The first example is find the solution of the recurrence relation given by an is minus 7, an minus 1 plus 10, an minus 2, which is equal to 7 times 3 to the power of n. Then you can see that let's do first the homogeneous part by making this one 0. When we are making this one 0, it becomes homogeneous. So what is the characteristic equation to the homogeneous part? So the characteristic equation to the homogeneous part is r squared minus 7r plus 10, which is equal to 0. Now to find the root to this characteristic equation, what are the numbers that their sum is minus 7 and their product is 10. So the numbers are minus 2 and 5. So r minus 2 times r plus 5. So the roots are r is equal to 2 and r is equal to minus 5. Hence, the solution to the homogeneous part. The solution to the homogeneous part is this one. An which is equal to c1 to the power of n plus c2 times minus 5 to the power of n. Now to find the solution to the non-homogeneous part, 7 times 3 to the power of n. So since 7d is 7 and 3 is not the root of the characteristic equation to the homogeneous part, the roots of the homogeneous part are 2 and 5, so that 3 is not the root, so that the trial solution will be c times 3 to the power of n. Now, substituting this trial solution to the given non-homogeneous recurrence relation, we have the following: 7 times 3 to the power of n is equal to c times 3 to the power of n minus 7 times c times 3 to the power of n minus 1 plus 10 times c times 3 to the power of n minus 2. Now, taking c times 3 to the power of n minus 2 as common, we obtain 3 square on this one. What remains when we are taking c times 3 to the power of n minus 2 was common. When we are taking this one, what's left here is 3 square, which is 9. And on this one, 3 times 7, which is minus 10 to 2. And what's left here is 10. So adding this one, you will get minus 2 times c times 3 to the power of n minus 2, which is equal to 7 times 3 to the power of n. So cancelling those similar terms, you will get that c is c minus 63 over 2. Therefore, the particular solution to the non-homogeneous part, will be this one. Hence, the general solution to the non-homogeneous linear recurrence relation is given by adding the homogeneous part and the solution to the non-homogeneous part. The solution will be this one. The solution is given by this one. Let's see another example. Find the solution to the recurrence relation given by an minus 4, an minus 1 plus 4, an minus 2, which is equal to the power of n. This one is also similar to the above question. Let's see. The characteristic equation to the homogeneous part, taking the homogeneous by making the non-homogeneous part is equal to 0. The homogeneous part, the characteristic equation is r squared minus 4r plus 4, which is equal to 0. So what are the numbers which their sum is minus 4 and their product is 4 is minus 2 and minus 2. So r minus 2 the whole square, which is equal to 0. So that is a perfect square. R is equal to 2 is the root of the characteristic equation with multiplicity 2. Since the root of the characteristic equation is repeated, so the solution to the homogeneous part, is given by this one. C1 to the power of n plus C2 n times to the power of n will be the solution. Now to find the solution to the non-homogeneous part, you can see that the one which makes the non-homogeneous part the exponential function to the power of n, the base 2 is the root of the characteristic equation to the homogeneous part. So that the trial solution to find the particular solution of the non-homogeneous part is this one. So c times n squared times to the power of n. So substituting this trial solution on the given non-homogeneous recurrence relation, you will obtain this one. C times n squared times 3 to the power of n and minus 4 c times n minus 1 the whole square times 3 to the power of n minus 1 plus 4 times c times n minus 2 the whole square times 3 to the power of n minus 2, which is equal to the power of n. Now, when we expand these terms, you will get the next equation. So c times n squared times 2 to the power of n minus 4, c times n squared minus 2 to the n plus 1 times 2 to the power of n minus 1 plus 4 times c n squared minus 4n plus 4 times 2 to the power of n minus 2, which is equal to the power of n. Now, let's take the common term on both sides. So c times 2 to the power of n minus 2 is a common one. So what's left here is 2 to the power of 2, which is 4 times n squared. 4 times n squared is left. What's left here is 2 times 4, which is minus 8 times n squared minus 2n plus 1. And the last one, what's left is 4 times n squared times minus 4n plus 4, which is equal to the power of n. So collecting those like terms, so when you multiply this one and collecting those terms which have the same power, so 4n squared minus 8n squared and 4n squared, you have this one. So, and the other one is 16n and minus 16n, and the number is minus 8 and 16 plus 16. So this term plus this term is 8 cancelled by this minus 8, and plus 16n is cancelled by plus 16n. So minus 8 plus 16 is positive 8. So that c times 2 to the power of n minus 2 times 8 is equal to the power of n is left. So that rearranging, we get the value of c will be this one. So that the particular solution to the non-homogeneous part will be 1 over 2 times n squared plus 2 to the power of n will be the particular. So therefore, the general solution to the given non-homogeneous recurrence relation will be the sum of the solution of the non-homogeneous part plus the sum of the non-homogeneous part, So c1 to the power of n plus c2 times n times to the power of n plus 1 over 2 times n squared times to the power of n will be is the solution of the recurrence relation. Let's take another example with the polynomial function. With the polynomial, it makes the non-homogeneous part becomes a polynomial function. So an minus 2, an minus 1 plus an minus 2, which is equal to 5 plus 3 times n. So the characteristic equation to the homogeneous part is r squared minus 2r plus 1, which is equal to 0. So factorizing this one, you'll get r minus 1 the whole square, which is equal to 0. So r is equal to 1 is the root of the characteristic equation with multiplicity 2. Hence, the root of the solution of the homogeneous part will be this one. The solution to the homogeneous part is this one, so which is c1 1 to the power of n plus c2 n times 1 to the power of n. Since 1 to the power of n is 1, so c1 plus c2 times n is the solution to the homogeneous part. Now, to find the solution to the non-homogeneous part, the one is the root of the homogeneous part, so that the trial solution to the non-homogeneous part will be n times n the power of n times n, which is n squared times n naught plus a1 times n. Since it is a linear function, it becomes the trial solution will also become a linear function, and n squared is obtained because of 1 is the root of the homogeneous part of the root of the homogeneous part. So that substituting this trial solution on the given non-homogeneous recurrence relation, you will obtain this one. So when you are substituting on the an part, n squared times a naught plus a1 n minus 2 times, when we are substituting on the an minus 1 part, 2 times n minus 1 the whole square times a naught plus a1 times n minus 1, and plus substituting on the an minus 2 part, n minus 2 the whole square times a naught plus a1 times a minus 2, a1 times a minus 2. So which is equal to 5 plus 3n. So you have this. So when you are expanding n minus 1 the whole square and n minus 2 the whole square, you will get this one, n square times a naught plus a1 times n minus 2 times n square minus n to n plus 1 times a naught plus a1 times n minus 1 plus n square minus 4n plus 4 times a naught plus a1 times n minus 2, which is equal to 5 plus 3n. This equation satisfies for every values of n. This equation works for every value. So that let's substitute n is equal to 0 and n is equal to 1. N is equal to 1. So when n is equal to 0 is substituted, you will get that you can see that n is equal to, when you are substituting n is equal to 0, this term becomes 0. What's left is 8 minus 2 times a1. This term becomes 0. And minus 2 times a naught plus a1, 0 minus 1 minus a1. And this term is become 0. 4 times a naught plus minus 2a1. So that rearranging that, you will get that a2 times a naught minus 6a1 is equal to 5 is obtained when you substitute n is equal to 0. When you substitute n is equal to 1, you will get 2a naught is equal to 8. You will get 2a naught is equal to 8. So a naught becomes 4 when you are substituting 4 here, which is becomes 8, and subtracting it from 5, you'll get 6a1 is equal to minus 3. So the dividing by minus 6, you'll get a1 is equal to 1 over 2. So the particular solution to the non-homogeneous part, becomes this one. Hence, the general solution to the given non-homogeneous linear recurrence relation is the sum of the homogeneous part and the non-homogeneous part. So it becomes this one. Okay, the last example is when the non-homogeneous becomes the product of polynomial and exponential function. And we have given two initial conditions to determine the coefficients of the solution to the homogeneous part. So what the equation is? The equation is an minus 6, an minus 1 plus 8, an minus 2. So the characteristic equation to the homogeneous part is r square minus 6r plus 8, which is equal to 0. So what are the numbers where their sum is minus 6 and their product is 8, which is minus 2 and minus 4. So r minus 2 times r minus 4, which is equal to 0. So r is equal to 2 and r is equal to 4 are the root of the characteristic equation. Hence, the solution to the homogeneous part becomes c1 to the power of n plus c2 for the power of n. Now, to find the solution to the non-homogeneous part, you can see that clearly the base for the exponential part is the root of the characteristic equation to the homogeneous part. So that with multiplicity 1, so that the trial solution to the homogeneous part, to the non-homogeneous part, will be this one. The polynomial function is linear, so that a0 plus a1 n is 1 times the product of 4 the power of n times 1 n is the power of 1, which is the multiplicity of 4 is 1. Now substituting this value, this trial solution to the non-homogeneous recurrence relation, substituting on the an part, substituting on the an minus 1 part, and substituting on the an minus 2 part, you'll get this one, which is equal to n times 4 the power of n. So taking for the power of n minus 2 from the whole part for the power of n minus 2 as a common, you will get n times a0 plus a1 n times 4 square. What's left here is 4 square when we are taking for the power of n minus 2. And on the next one, 6 times n minus 1 times a0 plus a1 times n minus 1 times 4 the power of 1 is left here. In the last one, 8 times n minus 2 times a0 plus a1 times an minus 2, which is equal to 4 the power of n minus 2, taking the 4 the power of n minus 2 as common, which is 4 n times 4 square is left. So cancelling this one by this one, cancelling the two values, you will get this equation. You will get this equal 16n times a0 plus a1 n minus 24 times n minus 1 times a naught plus a1 times n minus 1 plus 8 times n minus 2 times a naught plus a1 n minus 2, which is equal to 16. N is left. Now, this expression holds for all values of n. So substituting the values of 0 and 1 in particular, you will get two equations. So when you substitute n is equal to 0, you get a naught plus a1, which is equal to 0. When we substitute n is equal to 1, we get a naught plus 3a1 is equal to 2. So solving these equations from the first equation, a naught is equal to how much? A naught is equal to minus a1 so that substituting on this one, minus a1 plus 3a1 is equal to 2, which is 2a1 which is equal to 2. So a1 becomes 1, so a naught becomes minus 1. Hence the particular solution to the non-homogeneous part becomes this one, this one. N times a naught plus a1 n times 4 to the power of n, which is n times a naught is minus 1 plus a1 is 1, so n times n minus 1 plus n times 4 to the power of n, which is n times minus 1 times 4 to the power of n is a particular solution. Hence, the solution to the solution to the given non-homogeneous linear recurrence relation is the sum of the homogeneous part plus the non-homogeneous part. So which is C1 to the power of n plus C2 for the power of n plus n minus 1 for the power of n is the general solution to the linear non-homogeneous recurrence relation. But it is given two initial conditions to find the coefficients of the homogeneous part. So when you substitute n is equal to 0, it is 8. So C1 plus C2 is equal to 8. And when you substitute n is equal to 1, you will get 4 times C1 plus C2, which is equal to 22. So solving these two equations simultaneously, or substitute from this equation, we obtain that C1 is 8 minus 2. So substituting this one on the second equation, and here on this equation, you will get 4 times 8 minus 2 plus 2C2, which is equal to 22, which implies 4 times 8 is 32, minus 4C2 plus 2C2, which is minus 2C2, which is equal to 22. So C2 becomes 5. And substituting the value of C2 on the other equation, we will get C1 is equal to 3. Hence, the solution to the given non-homogeneous recurrence relation is an is equal to 3 times 2 to the power of n plus 5 times 4 the power of n plus n minus 1 times 4 to the power of n is a particular solution to the non-homogeneous recurrence relation. So this is all about today.